All right. Hello, everyone, and welcome back to day 4 of our lessons in introductory physics. This is just a quick review of what we talked about yesterday. And here we go, because this information is pretty foundational for what we're doing today. We're going to build on this today. So I wanted a quick review what we talked about just to make sure it's back in our brains after our break from yesterday. So here we have our 3 graphs. We're talking about how to find velocity given a position graph. And so here we have 3 different views of this position graph. So when we have a position time graph, position is on the y-axis, time is on the x-axis. We abbreviate position as x or sometimes s, but in this case we're going to be using x. So we can see our position time graph has a nice smooth curve that you can see in blue. And if we're interested in finding out the velocity, the average velocity between 2 points in the motion of a particular object, then we just take the slope of the line that connects those 2 points. But we can see as we get those points closer and closer together, so as the time interval between those points gets smaller and smaller, we end up taking what's called an instantaneous velocity. If we narrow the time frame, the time interval down to just a single point in time, and we take the slope of the line that's tangent to our position graph at that moment of time, then we have found our instantaneous velocity. And in fact, taking the slope of a tangent line like that is what's called a derivative in calculus. I think derivative is kind of a scary word if you've never taken calc before, but really it just means the slope of the line, how steep that line is at that one particular point in the curve. Okay, so at any point on a position time graph, the instantaneous velocity is equal to the slope of the line tangent to the curve at that point. Okay. Here's another picture that we ended up with yesterday. This is an example of a position time graph. We can see our variable x on the y-axis for position, t on the x-axis for time. We have this nice curve. So if we take the slope of those tangent lines at each of those different points, we can describe the not only the motion, but also the velocity of that particular object. So at A and B, the slope is positive, meaning the velocity is positive. At C, the slope is 0, so velocity is 0, meaning the object is not moving. And then at D and E, the slope of those tangent lines is negative, and so our velocity is negative. The object is returning back to where it started. Okay, this slide I didn't have. I don't think I had this in the PowerPoint yesterday. Maybe I did. I don't remember. But here are the 2 practice activities that you can use for the information that we covered yesterday: position graphs and interpreting what they mean, figuring out what the velocity is from a position time graph. Okay. So any last questions about those things before we jump into our next topic? Okay, Joshua, I see you have a question. Is all the physics we are doing going to be in a vacuum? Let me think. I would say the majority we are going to be ignoring air resistance. Yes. The majority of this we're going to be considering to be the ideal case for the sake of simplicity. There may be some cases where we would consider air resistance, For example, in a couple of days, once we start doing projectile motion, I'll probably show you a comparison between the motion of an object with no air resistance versus motion with air resistance, just so you can see what the differences between those things would be. But just off the top of my head, I would say most times we're going to be thinking about the ideal case. So no air resistance, and most of the time ignoring friction unless I'm specifically asking you to incorporate friction. Great. Okay. So let's move on. Today we're going to be starting to talk about acceleration. So average and instantaneous acceleration. And of course, there's the cat picture of the day. Law of cat acceleration. A cat will accelerate at a constant rate until he gets good and ready to stop. Okay, so if you have a piece of paper handy, or if you want to just type your answer into the chat, I want you to give a couple of these a try. We have, I think, 5. Give it a try, quick review questions for you. So these are all going to be position time or distance time graphs. Which one best matches the scenario? So in this case, Bryn walked away from the house. Which one do you think best matches? Good, I'm seeing a lot of answers coming in. That's great. Great, yeah. So all of you so far who have typed in answers seem to agree that A is the correct answer, right? Bryn walks away from the house. So the position, the distance from the house increases over time. Next question, Christian walked toward the swimming pool. Which picture best represents that scenario? Good answers. I feel like Family Feud or something. Good answer. Yeah, but I mean, good, good job. Yes, he's walking toward the swimming pool. So if the swimming pool is our origin, it's walking towards it. The position is getting closer and closer to 0. All right, next one. Anna ran toward the fence and then away. Which graph best represents that? All right, cool. So I saw some interesting things happening with this particular um, question, which is why I like it so much. So most of you probably said C, which is a valid answer, but B is also a valid answer. I saw one of you said B, and that's totally valid as well. It depends on what you choose as your point of origin. Right, so if the fence is your reference point, and then Anna runs towards the fence and then away, then C would be correct, right? Running toward the fence means running toward the origin point, the point of reference, and then away. But if Anna's starting point is your point of reference, then B could also be valid. There is a case for both. All right, next one. Ben stood still watching the others move around. Good, yeah, we all seem to agree on this one. C for cat, nice. Yes, C is our correct answer because his position is not changing over time, right? It's just that constant distance because he's just standing still. Good. Last one. All the children raced down the hill together away from the house. Which graph best corresponds to that? Good, yeah. That I like it. Yeah, so we're starting to see that our reference point does make a difference, right? You could make a case for A, absolutely. You could make a case for C, absolutely, depending on what your origin point is. In this case, I picked A, um, whereas the house is that reference point, um, because it's, it's explicitly stated in the question that there is a house. So I just chose that to be the point of origin. But you could absolutely make a case for D as well. Okay. So acceleration is our next step in terms of what we've been talking about so far. Position, velocity, and acceleration are all really closely connected to each other. So we talked about position and velocity yesterday. Acceleration is today. And yesterday we mentioned that velocity describes the rate of change of position with time, how quickly our position is changing. Acceleration describes the rate of change of velocity with time. So um, how fast is changing, if that makes sense. It's also a vector quantity. We give it the symbol A for acceleration, but lowercase a. Capital A is something different. It has the units of speed, or like a velocity unit, divided by a time unit. So meters per second gets simplified to be meters per second squared. Okay, so that's the most common unit that we'll see with that. It could also be feet per second, or miles per hour per second, depending on what makes the most sense for each scenario. But meters per second, or meters per second squared is the most common one that you'll see. There are actually 3 different ways that an object could accelerate. What do you think those 3 ways are? Positive, negative, or neutral? Good idea. Positive, negative, and constant. All right, I like it. Constant. Accelerate, decelerate, constant. Good. So probably the one that we are most familiar with thinking about, because we probably heard this word accelerate before, especially if you like drive a car or something. You've probably heard this word accelerate used in not physics class. So the most obvious way that an object can accelerate is by speeding up. That's typically the connotation for accelerate that we most often mean. But in physics, we don't have a separate word decelerate. We just also call slowing down an acceleration, because anytime the velocity changes, that's acceleration. And velocity could change by speeding up or by slowing down, right? That would, either way, you're changing how fast you're going. The third way is really the one that people tend to forget about most often. Okay, so remember, is velocity a vector or a scalar? Yeah, good. It's a vector. So what 2 things does something need to be a vector? Remember our supervillain, vector. What 2 things does something need to be a vector? Right, magnitude and direction. So those first 2 ways to accelerate, speeding up and slowing down, those correspond to the magnitude, right? How fast the object is moving. So the third way that something can accelerate is by changing its direction. Because if we change the direction, we've also changed the velocity. Driving 35 miles per hour north is not the same thing as driving 35 miles per hour west. right? You'll end up at a completely different place. You're going a different direction, you have a different velocity. So we can accelerate by either speeding up, slowing down, or changing direction. And all of those things are called acceleration in physics. Like I said, there's no separate deceleration word. So just like with velocity, we can have a couple of different kinds of acceleration. We're going to start off with average acceleration, which is an object's change in velocity over a period of time. So in that dashed green box, there is our equation for that. Average acceleration is that change in velocity divided by change in time. Remember that triangle symbol, delta, means the change in something. Okay, so V2 minus V1 over T2 minus T1. And here's just an example to cement it in your brain a little bit. If the velocity of a marble increases from 0 to 60 centimeters per second in 3 seconds, then its average acceleration is 20 centimeters per second, or 20 centimeters per second squared. Right? 60 minus 0 over 3 minus 0 gives us 20. And that's because the marble's velocity increased by 20 centimeters per second every second on average. Okay, so that's the way that we would use this particular equation. So we have to be really careful with this idea of acceleration compared to velocity. This is probably the most commonly confused idea in most students' heads that I found so far. Right? Acceleration and velocity are related to each other, but they're not the same thing. Velocity describes how an object's position changes with time. Acceleration describes how the velocity changes with time. Right? So velocity is how fast and in what direction the object is moving. Acceleration is how the speed and direction of the motion are changing. Okay, related to each other, but not the same thing. All right, here's an example. I want you to give it a try. An astronaut has left an orbiting spacecraft to test a new personal maneuvering unit. As she moves along a straight line, her partner on the spacecraft measures her velocity every 2 seconds, starting at a time of 1 second. Find the average x acceleration and state whether the astronaut's speed increases or decreases for each time interval. So take a couple of minutes. I'm going to pause the recording for just a moment. Take a couple minutes, think through this example, and then we'll come back together and go through the answer. Okay, so let's start working through these together. Hopefully your answers look somewhat along these lines. I have the answers there in the green box, and then the math part worked out on the bottom. So that first time interval from 1 second to 3 seconds, we'll look at that one first. So remember, acceleration is your change in speed, well, change in velocity over change in time. So that would give you 1.2 minus 0.8 divided by 3 minus 1. So 0.4 divided by 2, which is 0.2 meters per second squared. Okay, same basic idea for the other time intervals. From 7 to 5, our velocity at 7 seconds is 1.2. Oh, sorry, there's a kind of a typo in that equation, but it's okay. Our velocity at 5 seconds is 1.6 meters per second, and that time interval is 7 minus 5. So we end up with a negative acceleration in that case. And same format for the next two time intervals. Now, the question, remember, asked you if the speed was increasing or decreasing during that time interval. So we're going to take a look at the velocities. From 1 to 3 seconds, we went from 0.8 to 1.2 meters per second. So that difference was positive, and we increased in speed. Looking at this 5 to 7 time interval, we went from a velocity of 1.6 meters per second to a velocity of 1.2 meters per second. So our speed decreased. Okay, that should be fairly straightforward. The problem with thinking tends to come when we're dealing with these negative velocities. So let's take a look at those real quick. At 9 seconds, we have a velocity of negative 0.4 meters per second. And at 11 seconds, we have a velocity of negative 1 meter per second. So remember, speed and velocity are not the same thing. Speed is just the magnitude. It doesn't care about the direction. So if we're going from a speed of 0.4 to a speed of 1, we have increased our speed. And likewise in our thinking, if we're going from a speed of 1.6 to a speed of 0.8, we have decreased our speed. Okay, so in the chat, give me a quick, like a thumbs up or a smiley face or a yes if you feel pretty good about these. Great, good. Jared, I'm so sorry. I think that's crying. But I know you can cry a little bit inside. I'll accept that. Okay, so let's move on. Looks like we are feeling pretty good about these. Okay, so a thing to keep in mind when we're thinking about velocity and acceleration, since they are so closely related to each other, it is okay to mix and match the signs that our velocity and acceleration have. They don't have to have the same sign as each other. So it is possible to have a positive velocity and a positive acceleration. That would mean you're moving in the positive x direction and speeding up. You could have a positive velocity, but a negative acceleration, which means you're moving in the x direction and slowing down. Those things tend to make sense in our brains. It's a little bit weirder to visualize what's happening when we're thinking about negative velocity again. So let's take a look. Negative velocity and positive acceleration means that you're moving in the x direction, but you're slowing down. And it seems weird to think that you have a positive acceleration, but you're slowing down. But remember, acceleration is a vector. The direction corresponds with the sign. So if you're moving in the negative x direction, but you're slowing down, that's kind of like there's another force kind of pushing you back towards the positive x direction that's making you slow down. And that force that's pushing you back towards the positive x direction is the positive acceleration. Not that force and acceleration are the same thing, but it's to visualize it. I think that can help sometimes. So moving in the negative x direction and slowing down means you have a negative velocity but a positive acceleration. And if you have a negative velocity and a negative acceleration, then you're moving in the x direction, but you're speeding up, right? Because that negative acceleration is kind of boosting you even more towards the negative side. So we can't just look at the sign of acceleration to know if it's speeding up or slowing down, right? You can see that first bullet point and the third example there both have a positive acceleration, but in one case the object is speeding up and in the other case it's slowing down. And likewise, that second and fourth one both have a negative acceleration, but in one case it's slowing down and in the other case it's speeding up. So we can't just look at the sign of acceleration to know what it's doing. We have to compare it to the sign of the velocity. If the two signs are the same, positive and positive or negative and negative, then our object is going to be speeding up. But if they're opposite signs, positive and negative or negative and positive, then the object is going to be slowing down. Okay, so that's that's a really important point to remember. If you take notes on this information, maybe jot that down and put a star next to it if that's going to be tricky for you to remember. But pay attention to those signs compared to each other, not just by themselves. Okay, do we have any questions about this, this slide? We're going to use this idea in a real life example momentarily. Oh, good. No questions. Okay, great. Let's put this into a real life scenario then. Okay, what are the signs, positive, negative, or zero, of velocity and acceleration in these cases? So if you have a piece of paper, jot down your answers. You can type it in the chat if you want to. Let's think about each of these 5 cases. I'll give you a moment to think. All right, so let's go through some of these answers and see how you guys did. Okay, so this first case, backing out of a parking space. Since we're backing up, our velocity is negative. Again, we always kind of assume, well, we usually assume that forward is positive and backwards is negative. So velocity is negative in that case. The acceleration could go several ways depending on what part of your backing out you're thinking of. If you're thinking of at the beginning of the backing out while you're speeding up backwards, then your acceleration would also be negative. But if you're thinking, I'm almost done backing up, now I'm slowing down, then your acceleration would be positive in that case. All right, B, driving forward on a highway at a constant speed. I mean, I would hope that you would always drive forward on a highway. I just wanted to specify in case you're thinking like Fast and Furious or some epic police chase where you're driving backwards at 90 miles per hour and magically avoiding all the cars. But anyway, you're driving forward because you're a great, safe human being on a highway at a constant speed. So our velocity driving forward is positive. But since we're going at a constant speed, our acceleration is 0. Our speed is not changing either in magnitude or direction. And so since our velocity is not changing, our acceleration is 0. C, speeding up to pass someone. Again, I'm hoping that you're doing that driving forward, so your velocity would be positive. And since you're speeding up forward, your velocity is increasing, so your acceleration is positive as well. D, slowing down because the next traffic light is red. Again, assuming that you're driving forward. Then your velocity is positive, but your acceleration is negative because your velocity is decreasing. And then E, your car, the moment the traffic light turns green. So at that moment, your velocity is 0 because I'm assuming that you've stopped at the red light, but your acceleration is positive because your velocity is going to be increasing. And a lot of you might think that it's not possible to have a 0 velocity but a positive acceleration. And it absolutely is possible. And in fact, it's kind of mandatory because if a 0 velocity necessitated a 0 acceleration, then nothing would ever start moving. You like literally would not be able to start moving if your acceleration had to be 0 if your velocity was 0. Right, so it's absolutely possible for your acceleration to be positive or negative and your velocity to be 0. Okay. It just means that your velocity is changing somehow. Does that make sense? Are we feeling pretty good about these quick check things? Yes, great. Like a change in direction. Yep, absolutely. When we're changing direction, our velocity is going from positive to negative or negative to positive, and it momentarily passes through 0. The velocity can be momentarily 0, but our acceleration is not. Absolutely, Joshua. Okay, great. So instantaneous acceleration. Remember, yesterday we talked about average velocity and instantaneous velocity. Today is average acceleration and instantaneous acceleration. And it's the same basic idea as with velocity. The limit of the average acceleration as the time interval approaches 0, or the instantaneous rate of change of velocity with time, right? It's that instantaneous part that we're most interested in for instantaneous acceleration. But this is actually the acceleration that we will be dealing with most commonly. So usually I'll just call it acceleration. But yeah, it's a very similar analogy as with instantaneous velocity versus average velocity. So remember, instantaneous velocity, we said yesterday, was dx over dt. And that dx dt is a derivative, which is a fancy way to say the rate of change of something. So our instantaneous acceleration is the limit, as our time interval gets smaller and smaller and smaller, of our change in velocity over change in time. And that's a derivative as well, right? So this is actually the derivative of velocity over time, dv dt, or dvx, since we're just dealing with horizontal things right now, dvx dt. But we already knew that velocity was dx dt. So if we have the derivative of a derivative, we call it a second derivative. And we put that little 2 symbol next to the d and next to the t there. So d2, or d squared x over dt squared, is a second derivative because it's a derivative of a derivative. Yay, calculus. And somebody had the question yesterday, I don't remember who it was, but about if there's a derivative of acceleration. And yes, there is. So we start out here with position. The derivative of position is velocity. The derivative of velocity is acceleration. The derivative of acceleration, if your acceleration changes over time, then that's called a jerk. If that changes over time, then it's called a jounce or a snap. And then, because physicists are just so dang funny, the derivative of a snap is a crackle, and the derivative of a crackle is a pop. Now, I don't know if you guys, like, if these mascots existed for you, but when I was a kid eating Rice Krispies, they're the mascots of Rice Krispies. And they're named Snap, Crackle, and Pop, which is why physicists thought, hey, let's just do that for these really obscure derivatives that nobody ever really uses. So they're actually called Snap, Crackle, and Pop, these derivatives, which is kind of funny. And another kind of funny story about this, Dr. Harris, who he was here in the video on the first day. He's the professor who's kind of helping oversee this class. But he told this story about how one of the scientists that he worked with actually was one of the ones who discovered that the universe is accelerating. Its expansion is accelerating, but it's not accelerating at a constant rate. And so since the rate of the universe's expansion is changing, that means it's called a jerk, the universe's jerk. And so the scientist who discovered it was being interviewed by this newspaper and talking about this this jerk that's happening in the universe's expansion. And the newspaper headline that they published this article as was "Astronomers Discover Cosmic Jerk," and it had this big picture of him right next to the headline. And I just thought that was the funniest thing ever. And so did he. He like framed the newspaper article that looks like it's calling him this cosmic jerk. But that's actually what it's called when the acceleration of something changes. So I just thought that was funny. Anywho, moving on. Okay, so yesterday we did our position time graphs, or our XT graphs, but we can also create velocity time graphs and acceleration time graphs. These three concepts are all related to each other because they're derivatives of each other. So since they're all related to each other, their graphs are all related to each other. Yesterday, remember, we learned that the slope of a position time graph gives us velocity. And since acceleration is the derivative of velocity, the slope of a velocity time graph gives us acceleration, right? Because a derivative is just a fancy slope. And they're also related to each other in another way too. We'll get there next week, but we'll just focus on the slopes today. So I'm going to do a couple of examples of setting up these graphs and how they connect to each other. And I have 3 different scenarios that we'll go through. So our first scenario, an object moves away from the origin at a constant speed. That's what we're going to try to graph. So when I set up these types of graphs, I set them up in stacks like this because I think that helps show how different portions of the graph relate to each other. So how the position and velocity and acceleration relate to each other. You can also draw them side by side if you want to, but I will tend to draw them in stacks like this just for visual connection purposes. So on top we have our position time graph. In the middle we have our velocity time graph. And then on the bottom we have our acceleration time graph. So if the object is moving away from the origin, that means its position is increasing. I didn't necessarily specify that it's moving forward, but I just assumed that it was. Okay, and it's moving at a constant speed. So I'm just going to draw these dotted lines wherever something important is happening in our position graph. For example, the end of motion right there. So we can see in this position time graph, the slope of this line is positive and constant, right? The slope is not changing, which means the velocity is positive and constant because the velocity is equal to the slope of this line. Now I didn't give you numbers because right now I'm just interested in shapes. So disregard numbers for a few moments. But when we have a positive constant velocity, it would be a flat line, a constant line at some positive number, whatever is equal to the slope of that line. We can see here the slope of a horizontal line is 0 meters per second per second. So our acceleration is 0 meters per second, or 0 meters per second squared. So here's our stack of graphs for this scenario. Right? Our position graph was a diagonal line, our velocity graph was a flat line, and our acceleration was a flat line at 0. Because those are all, relating to the slopes of the graph above it. Okay, next example. A dog runs away from you at a constant speed, then walks back to you. So again, here's our stack of graphs. The dog is running away from you. So that's a pretty steep part of our position curve because he's changing his positions very quickly. Right, so a pretty steep slope there, but then the dog is walking back to you. So the slope is not as steep there because he doesn't cover as much distance each second as he's walking back to you. So we can see there are a couple of interesting points, or a couple of sections, I suppose, of our position time graph. Right, we have that first section where we have the really steep slope, and then the second section where we have a less steep slope, and then motion stops. So I drew 2 dotted lines down for this graph. So in that first section, slope is positive and constant. So velocity will be positive and constant in that section. And then the second part, the slope is negative and constant. And so our velocity will be negative but constant. All right, so in that first part of our graph, where the slope is positive and constant, we have a positive constant velocity. And then it changes to have a negative slope. But remember, the slope there isn't as steep. So our velocity graph won't be as far down in the negative axis. But say, in the first section, you might have a slope of 2. Then the second section might have a slope of -1. Right? They're not the same magnitude, so they're not the same distance from the axis. But when we look at our velocity time graph, velocity starts positive and constant, and then it goes negative and constant. Both of those sections are horizontal lines. Well, the slope of a horizontal line is 0, so our acceleration is 0 meters per second throughout. And that green line should go all the way to the dotted line. That's just a typo on my part. Sorry about that. So yeah, even though our velocity has like these 2 different steps to it, the slope of both of them is 0. So our acceleration is 0 the whole time. All right, next example. You throw a ball straight up and it comes straight back down. So here is our stack of graphs, and we're going to draw the position first. So remember, we talked about this yesterday. Just because the position curve is moving forward on our graph, that does not mean we're throwing the ball forward. That just means that time is passing. And what we're doing is we're throwing the ball straight up in the air and then catching it again. It's coming straight back down. Well, as the ball is going up into the air, it's slowing down until it reaches the top, and then it speeds up as it falls back down into your hand. So that's what's happening there in this position time graph. And so I drew our dotted lines there, one halfway through our curve where it's changing direction. That's an important thing to notice. And then once again when the motion is ending. So if we look at that first part of our position time curve, we can see that the slope is positive, but it's decreasing as we move our hand, or if you hold up a pen on the computer screen and like move your pen along the curve, it's flattening out. Right? So our slope starts positive and decreases until it reaches the top where it's 0. Right? The slope of a horizontal line is 0. And then it gets increasingly more negative as you keep moving along your time axis. How do we draw that in terms of velocity? Well, something like this. Right, we're starting with a positive velocity, but it's decreasing. So our velocity curve goes down, crosses 0 right there at the dotted line where our ball is changing direction, and then gets increasingly more negative. So when we have an actual curve as our position graph, we'll end up with a diagonal line as our velocity graph. And since our velocity graph is not just a horizontal line, right? It's positive and decreasing, then 0 at the dotted line, then increasingly negative. The slope of our velocity graph is negative. It's a constant negative. And so our acceleration graph is a constant negative number. Now, if you've taken physics before, then you might know what that acceleration actually is. If you know what that acceleration is, go ahead and type it in the chat. Good, yeah. G, negative 9.8, negative 9.81 meters per second. Thanks for adding in your units there. Meters per second squared would be our units for acceleration. Gravity, nice, yeah. So our negative acceleration there, is our acceleration due to gravity. And that number you'll be very, very familiar with in a couple of days, negative 9.8 meters per second squared. So gravity is pulling that ball down with a constant acceleration, and since it's pulling it down, it's negative. But good job, guys. I see that you had some questions or comments while I was going through some of these examples. So give me a moment to quick look through the chat and see if there are questions that I need to address. Joshua, yes. Don't be a third derivative of position with respect to time. Don't be a jerk. Yes. Okay. But shouldn't we draw a point when the dog changes direction, considering the dog changed its motion in the acceleration graph? We did draw the point where the dog changes direction, and that was the peak of our position curve, because he's going forward and then backwards, and we see that reflected by the fact that he is moving back towards that axis, the x-axis. If we're given equations, we can just do the derivative and graph the derivative equations. Yes, you can, Joshua. If you know how to take derivatives already, if you've taken calculus, then you can absolutely just calculate it mathematically. And I'll actually be teaching everybody how to do that next week, because I know some of you probably haven't seen that yet if you haven't taken calculus in high school. But it's not terribly difficult, and like I said, I'll be teaching everybody how to do that next week. Gabriel, you're right. Yes. You said, I mean, instead of drawing a straight line in the acceleration time graph, we should cut it in the exact moment when the dog comes back. Theoretically, it can't change its movement without an acceleration. That's absolutely right. A dog can't just instantaneously go forward and then come back. That's not physically possible. This would be like an idealized case where, just for the sake of simplicity, we're ignoring the fact that the dog slows down a little bit while it changes direction and then speeds up a little bit while it comes back to you. That's absolutely true. Yes. Good observation, though. Okay. Casey, I see you have a question here about needing to keep the math introductory. So remember, the purpose of this class is to just introduce you to all of these, well, many of these different topics that you'll see in Physics 1 when you take it at college. So I do want to introduce these calculus concepts to you, even though calculus isn't a prerequisite for this course or anything like that. I don't want the first time you see it to be when it's in a high stakes environment like a college class. So I want to introduce it to you so that you can see it and start thinking about it. But if you don't understand it right away, it's okay. You have plenty of time to learn. Idealizing things is needed to keep the math introductory. Idealizing things is, yes, it is kind of needed to keep the math introductory. You'll find that the farther you go into your physics career, the less and less idealized the situations become. And then, in your non-physics 1 classes, like physical mechanics or orbital mechanics, or I took space flight mechanics as well. Those types of classes are where they would teach you how to take into account all of these various factors like air resistance and turbulence and atmospheric drag in different parts of the atmosphere and that sort of thing. But that's not a physics 1 level idea. That's the more advanced physics classes. Okay. So I want you to grab a piece of paper. You can't really sketch things in the chat. So grab a piece of paper, and I want you to try to sketch the velocity time and acceleration time graphs from this position time graph. You don't need numbers, just make a quick sketch of what you think the shapes of the graphs would look like. I'll give you a moment to think through that. All right, so hopefully your graphs look something related to this. This one didn't have it in a stack, it has it side to side. So it's a little bit, I think in my mind, a little bit more complicated to relate the sections together. But we can see in this position time graph, at first, the slope of our tangent line here would be positive. So our velocity starts out positive. But then at the top of this first hill, our tangent line becomes flat, right? It goes, so our velocity decreases to 0. Right here you can see it crossing the axis at 0. And then it's negative as it looks like it's going down that hill in our position graph. So it goes down to a negative velocity. But then our slope of our tangent line decreases in negativeness to flat when it's at the bottom of that at that hill. So our velocity again crosses 0 at that point. And then our velocity, our tangent line gets more and more positive as it goes along this last part of the position graph. So our velocity gets more and more positive until it's a constant positive value right there at the end. Our acceleration time graph, we're going to take the slopes of our velocity time graph. So at first, the slope of our velocity time graph is very negative. You can see very negative, but constant in our acceleration. And then it jumps up to very, very positive, but constant. And then it's a little bit less positive, but still constant. And then at the end of our velocity time graph, it's 0. Okay. So how did we do on that example? I know this was a little bit more challenging than the ones that we did together. So how about this? On a scale of 1 to 5, 5 being I totally get this, 1 being what the heck am I looking at? How are you feeling about this? Okay. 3 is 5. Went from 5 to 2 real fast. That's accurate. Yes, this was quite a bit of a step up, and I think it will be more helpful as well once we have numbers that we can actually like calculate slopes and graph them with numbers. 2.5, great. How do we feel about just going from position to velocity? Okay, it looks like for the most part, for those of you who are participating in the chat, it looks like for the most part, we're feeling pretty good about going from position to velocity. We might just need a little bit more practice visualizing these things. And I will also say that when the position graph is curved like this, that it can be a little bit more challenging to think about. So then I'm guessing for those of you who feel a little less confident in this, the issue would be going from velocity to acceleration graphs. But we have to approach them basically, we approach it the same way we do going from position to velocity. We're just taking the slope of each different section. So the kicker of this is you need to be able to draw the velocity graph correctly in order to draw the acceleration graph correctly. And that's really the downside when these things are so closely related to each other. But I do have some resources that will be helpful for you. So let me go ahead and and show you this bonus problem. Okay, I do want you to give this one a try if you feel like you struggled with the previous one, because I think this one is a little bit simpler since it doesn't involve curved sections. They're all straight line sections. So again, I want you to sketch the velocity time graph and the acceleration time graph from this position time graph. So you can actually calculate the slopes of these different sections. And we have some time left before we need to finish for today. So I'm going to pause the recording again and give you a couple of minutes to at least get started by drawing your velocity time graph. Okay, so go ahead and give this one a try. Okay, so let's think through this example. We'll just talk through it. I'll talk through it because I'm the only one talking. Whatevs. So the first section of our position time graph, you can see it's flat at 0. That means that our position is not changing. So we're just standing still. The slope of that portion of the graph is 0 because it's a flat line. So our velocity graph would be a flat line at 0 from the beginning until 2 seconds. The next section of our position graph is a downward slope. You can see we're going from a position of 0 to a position of -3 down here. Down here. And so our rise is -3. And we're doing that in 1, 2, 3 seconds. So our slope for this section is -1. On your velocity graph, you would draw a constant flat line at -1 from 2 seconds until 5 seconds. The next portion of our graph is this one right here. This is going to be a positive slope, so our velocity will be positive. We're going from a position of -3 all the way up to a position of 2. So that's a rise of 5, and we do that in 2 seconds. So 5 divided by 2 is 2.5. The slope of this line is 2.5, so you would draw a flat line on our velocity graph at 2.5 from 5 seconds until 7 seconds. And then for this big chunk right here, from 7 seconds until 12 seconds, our position is not changing. So again, we have a velocity graph flat at 0 from 7 until 12 seconds. The next part of our graph is a big negative slope. So we're going from a position of 2 to a position of -6, and that's a difference of 8. And we're doing that in 1, 2 seconds. So the slope of this part of the curve is -4. Okay. So on your velocity graph, you draw a flat line at -4 from 12 until 14 seconds. The next part of our graph right here, we're going from a position of -6 to a position of -2. That's a change of 4 meters. And we're doing that in 2 seconds. So the slope of this part of the curve is 4/2, or 2 meters per second. So our velocity graph would have a flat line at 2 from 14 until 16 seconds. Then from 16 to 18 seconds, we'd have another line at 0 on our velocity graph. From 18 to 19 seconds, we're changing our position from -2 to 0. So that is a change of 2 meters in 1 second. So the slope of this portion is 2. So we'd have our line on our velocity graph at +2 from 18 to 19 seconds. And then we'd finish it off with a flat line at 0 on our velocity graph from 19 to 20 seconds. Okay, sorry I didn't have a chance to draw that out on the slides yet, but just talking through that, does this example make a little bit more sense? I know that was just the velocity graph. Okay. Okay, great. So hopefully you were able to like sketch that velocity graph along with me as I was talking. Use that velocity graph to try to sketch an acceleration graph on your own. We'll start here again on Monday, and I'll have drawn out for you then um, a, a velocity graph and an acceleration graph so you can check how you did. But this would be a great one to practice because you can actually work with real numbers as opposed to just shapes. I have some other resources that I think you should try this weekend as well. They're not posted on Canvas yet, but they will be as soon as I get home and have a chance to scan them and upload them. But they're going to be called Motion Graphs Practice 2 and Stacks of Graphs. So this Motion Graphs Practice 2 worksheet is going to go through just drawing velocity graphs from a position graph. And then the stacks of graph goes through all three. So position, velocity, and acceleration. And it has them set up in stacks like I did in the example problems. So the stacks of graphs, I definitely recommend that you give this one a try. There are so many different scenarios and examples, and I just think it'll really help get this conceptual understanding a little bit better in a really wide array of possibilities. So again, those will be posted today when I get home, and I will post the answers to them on Monday. So that will give you a couple of days to think through them, give them a try on your own, and then we can talk about them in class again on Monday if you have any questions about them. Okay, any questions, comments, concerns about today, the material that we talked about today? Let me go ahead and look at this chat. Gabriel, you asked this velocity time graph would look with only horizontal lines, right? Yes, for that bonus problem that we were doing, it would only have horizontal lines. And then Joshua, you said the acceleration time graph is easy from that. It should be easy from that. Would it be more correct on the acceleration graph to just draw a line or draw the dots of instant acceleration when it changes? You could do it either way, and I'm just gonna leave it at that because your individual professor might have a preference. And I'm not your professor. I'm just introducing you to these ideas. So either way is fine. If you draw like a solid line or dotted lines, that's up to you. Why is there a milk bottle on the chalkboard? Cats shouldn't be drinking milk. You know, there's that. But people also shouldn't be drinking Mountain Dew, and we do. So there's that. True, milk squared. Yeah, that changes everything. That's like maybe like a milk ice cube. Square milk. I guess that'd be milk cubed. Huh. All right. Well, if there are no other questions, comments, concerns, we will call it here for today. We'll pick up here on Monday, going through the answer to that last bonus problem, and then moving on with more acceleration, motion in one direction before we jump into projectile motion later on in the week. So I'll be around hanging out for a couple more minutes if you guys have any questions about today or about college life, that sort of thing. Quick reminder though, please make sure that you do the pre-test that's posted on Canvas. That is, the deadline for that is tomorrow at 11:59 p.m. And also remember, tomorrow at 10 a.m. is our optional enrichment activity, first year college experience from some really knowledgeable people at Florida Tech. The link to that has been posted on Canvas in an announcement, so check that out if you would like to do so. Thank you so much for joining us today, and have a great weekend.